Today we're going to take a look at specific heat, what that concept is, and how to use it in calculations. Specific heat can help us answer questions like how much heat can something absorb or release. Specific heat is defined as the amount of energy it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. So for example, if we had a block of, say, aluminum, okay, if that block measured 1 gram of aluminum, the specific heat is the amount of energy, so the amount of Q that we need to add to it to raise its temperature 1 degree Celsius. So for instance, going from 25 to 26 degrees Celsius. So whatever that amount of energy is that we have to transfer to do this, that's called its specific heat. It is called specific heat because it is specific to each substance. Every substance is going to have its own value. Now the units for specific heat are joules divided by grams times degrees Celsius. It is a combined unit, similar to what we've seen with density, which was mass over volume, or grams per milliliter. So the joules are the part that measures energy, and it's the amount of energy to raise each gram by 1 degree Celsius. So it's joules per gram per degree Celsius. So that's why those are on the bottom there. So this is our units for specific heat. We have to use all of them to communicate specific heat. We can't just use one. So on your paper, you're going to jump down to the second table there, and we're going to do this a little bit out of order on your paper, but I want to talk about these specific heat values first and what they mean. So we've got 4 different substances listed here: glass, aluminum, plastic, and styrofoam, and we can see their specific heat values. So what that means is that, for instance, glass takes 0.84 joules of energy to raise 1 gram of it 1 degree Celsius. Now, we define specific heat by 1 gram and 1 degree Celsius so that no matter what the chemical is, we can compare them to each other. So the only value that's changing is those numbers of joules. We can see aluminum is a little bigger, plastic is higher, and styrofoam on this list is our largest one. Specific heat values don't have a very big range. Some of them are less than 1, some are a little bit more than 1. A few of them can be higher, but there's not a very big range of numbers there. So what does it mean? Glass having a lower specific heat means that it's able to absorb energy or transfer energy really well, really easily. It doesn't take as much energy to heat it up or cool it down. Styrofoam, however, being a higher specific heat, would take more energy, so 1.50 joules versus 0.84 for a glass, to heat up. So if I want to heat up a chunk of styrofoam, it's going to have to absorb more energy to actually change its temperature, to raise its temperature, than, say, glass would. So we use different materials for different reasons. Glass is great for things that need to transfer energy, but styrofoam is good for things that want to insulate, right? That we want to use for insulation so that we don't get as much heat transfer. So underneath, when a specific heat of a substance is low, it does not take as much energy to raise the temperature. And when substances have high specific heat, it takes a lot of energy to raise their temperature. So looking at an example, comparing 2 more, we've got water versus concrete. So think about it. Which one would require more heat to change its temperature? And our answer should be water. So water takes 4.184 joules of energy to increase a gram of that water by 1 degree Celsius, where concrete only takes 0.88 joules of energy to heat up the same amount by the same temperature. So when you go in the summertime and you step on concrete, it's going to be really, really hot. It's able to heat up to raise its temperature very easily by absorbing less energy to raise its temperature. But water, it takes a lot of energy to heat it up, to change its temperature, to raise its temperature. So for 1 gram of concrete, we only need 0.88 joules, but for water, we need 4 or 5 times that amount just to get it to raise 1 degree Celsius. But that's good. We want to have a nice cold pool in the summer, so we want water to stay a lower temperature. So how are we going to use this? We're going to use this equation called the specific heat equation. This is back at the top of your paper. So we're going to put this equation in the box, Q equals MC delta T. So that triangle next to the T is a Greek letter delta, and it means change, so we know. So let's break this down. All the letters in yellow are our variables, and then in parentheses at the end is our units of measurement. So Q is the amount of heat energy in joules. We're familiar with that by drawing our heat flow diagrams, Q in and out, when we measure that in joules of energy. M is going to represent mass in grams. We've used mass before in our density equation, and we're going to use G for grams for that one. C is that, and it should be lowercase c, I'm sorry about that, is the specific heat. So that is our number of joules per gram times degrees Celsius. Okay, so that's key here. This C is not Celsius, it's specific heat, and it has these units, okay, because it's a variable, not a unit. Delta T is that change in temperature measured in Celsius. So that's where we see our degrees Celsius. So when we talk about the change in temperature, if I add heat to something, it's going to raise its temperature. So we don't really care about where it starts or where it ends. We want to know what the difference is. So to find that difference, we're going to do the TF minus TI. These F and I represent final and initial, or final and starting. So we want to take the final temperature where it ends and subtract the starting temperature to be able to use that. So this is our equation, Q equals MC delta T. These are being multiplied by each other, okay, M times C times delta T. So we're going to take a look at some examples and see how to work this out. All right, before we get into our example calculations, let's talk about positive versus negative values. So as we've explored so far, as something gains heat, we call that an endothermic process. We're adding energy to our system. And if we lose heat, then we call that an exothermic process. Now, with an endothermic process, since we are gaining heat, our Q value is going to be positive, as we've practiced with our heat flow diagrams. And if it's losing heat, an exothermic, our Q value is going to be negative. Now, the other thing we can look at is our change in temperature. If something gains heat, then its temperature is going to go up. It's going to gain in temperature. So our change in temperature should be a positive change. However, if we lose heat, if heat goes out of our substance, the change in temperature, the temperature is going to drop. So our change is going to be negative for that. Now, M and C, M is our mass, and we cannot have negative values for mass. Mass must be a positive value because mass represents the amount of particles or amount of stuff you have there, and you can't have negative stuff. You can't have not stuff. It doesn't quite make sense. So it has to be positive, and specific heat, our C value, always has to be positive because it is defined as a positive value. It's the amount of energy gained when we heat up that substance 1 degree Celsius. So it has to be positive. So keeping that in mind, we're going to take a look at some examples. When we do these examples, I'm going to show you some strategies to help you think through them, and we're going to draw some heat flow diagrams for them so we can determine which direction our Q is going, where heat is going, and if things should be positive or negative. So in this question, a 2-gram sample of a metal was heated on a hot plate from 15 to 40 degrees Celsius. Missing those degree signs. It absorbed 52 joules of energy. What is the specific heat? So we're going to start by drawing our heat flow diagram. A very simple one. So our sample is of a metal, and that metal is what all these measurements are about, right? How much energy absorbed, what the specific heat is, its temperature change, all of that. So metal is going to be our system. Our hot plate is in our surroundings, so we're going to put that out here. Now, our energy goes from the hot plate to the metal, since our metal is absorbing energy. So that means our Q should be a positive value. And this should be an endothermic situation. Okay, so now that we have that defined, we know it's going to be positive. That's going to help. So now we want to actually calculate what's going on. So let's check it out. In our question, we're given 2 grams of our sample. We know the temperature goes from 15 to 40 degrees Celsius, and it absorbed 52 joules of energy. And we are looking for the specific heat. So what I like to do to get started is list my variables so that I know I can match up all those numbers to these variables. Okay, so our Q value is, Q represents energy or heat. So it said 52 joules of energy, and we know it's going to be positive because it's endothermic, so we're going to leave it positive. M represents mass, and mass is in grams, so we're going to put 2 grams there. C represents our specific heat. Now our question is actually asking for specific heat, so we're just going to put a question mark there. And delta T is that change in temperature. Again, the final minus the starting. So our final temperature is 40 because it says it goes from 15 to 40. So we're going to do 40 minus our starting 15, and that's going to give us 25 degrees Celsius. Now we're going to take a look at our equation. Q equals MC delta T, which are all being multiplied. So if we want to solve for C, then we need to isolate it. So we do that by doing the opposite operation on the other 2 variables. So we're multiplying them, we got to divide them. Opposite. So we're going to divide them on both sides. M and delta T are going to cancel. So our specific heat is equal to Q over M delta T. And then we can go ahead and plug in our values. Our Q value is 52 joules. Our M is 2 grams. And our delta T is 25 degrees Celsius. Now I like to put the bottom in parentheses just to show that those should be multiplied before we divide. Okay, so be careful with that. And we can go ahead and calculate. Practice with your calculator and see what answer you get. So we should get 1.04 for our value. And let's take a look at our units. We have joules, grams, and Celsius. None of those match, so none of those are going to cancel. So we're going to write them all down in their placement as we see them on the problem. And those are the units for specific heat. So those are the correct units. That's what we want. So what this means is the specific heat of whatever metal this is 1.04. It takes 1.04 joules of energy to raise 1 gram by 1 degree Celsius. And if we had a table of values of different metals, we could actually look up which one matches, and we could identify our metal using that as well. So let's take a look at another example. All right, this one says how much energy or how much heat is needed to raise the temperature of 10 grams of a substance from 40 to 60 degrees Celsius if the specific heat is 3.8 joules per gram degree Celsius. So the question is asking for how much heat, all right? So let's do our quick little diagram just to think through our positives and negatives. So this is talking about some substance. That's going to be my system. And then we don't have anything. It's not telling us much about its surroundings. We can always just put air or the container, things like that. Now our substance is raising its temperature, and it sees how much heat is needed to raise that temperature. So the substance must be gaining heat from its surroundings. It's going in, which means our Q should be positive. That's endothermic. So now let's do our list of variables. Q equals MC delta T, and we'll match these up. So we've got 10 grams. That's going to be our mass because grams measure mass. We've got 40 to 60 degrees Celsius. So we do final minus starting. So 60 minus 40 to give us 20 degrees Celsius for our change. The 3.8 is that joules per gram degree Celsius. That's our specific heat. Has those really specific complex units. And then our question is how much heat. So we're looking for what Q is. How much heat is exchanged here. Since our equation is already set up with Q isolated by itself, we don't have to rearrange it. We're just going to plug in our numbers. Now I put these in parentheses only just to separate the units out, make it kind of look cleaner. But you don't have to type them in when you calculate. You don't actually have to write the parentheses. I just like to. So if we multiply this out, we should get 760 for our answer. So it's always good to check with your calculator, make sure you're getting your numbers in correctly. Now in terms of our units, we can look at what matches and what would cancel. So we have grams and grams. We have Celsius and Celsius. Those would all cancel. We'll be left with joules. Joules are a measurement of energy, and Q is our energy or heat. So we are good there. All right, we're going to do one last example. So a 50-gram piece of hot metal is put into cold water. So we can already imagine our hot metal put into cold water. And I made the metal our system in this case. And the reason is because the metal transfers 5,000 joules of energy to the cold water. So we're focusing on what the metal is doing. The specific heat of the metal is 6 joules per gram degree Celsius. What is the change in temperature of the metal? So everything is in the context of the metal, so that's the part we want to focus on. Now, the hot metal is going to give the cold water its energy. So that means Q is going to be negative for this question. Going to be exothermic. But if we look in our setup here, it says the metal transfers 5,000 joules of energy. That's our Q value. It doesn't show it as negative. We have to make it a negative value. Okay, so thinking through your heat flow diagram to start is going to help you remember when to make something negative. So let's list our variables. Our Q is going to be negative 5,000 joules. Our mass in this situation, 50 grams. And it gives us 6 joules per gram degree Celsius. That's our specific heat. So we want to figure out what that change in temperature is. We don't really care what the starting or the final temperature is. We just want to know what the change is, that difference. So looking at our equation, Q equals mc delta T, we want to solve for delta T. So that means we're going to divide by the other two variables on both sides. So delta T equals Q over mc. All right, I'm going to plug in our numbers. Negative 5,000 joules divided by 50 grams times 6 joules per gram degree Celsius. And if we go ahead and calculate, making sure that bottom part in the parentheses, you do want to go ahead and make sure that's in parentheses because we want to divide by both of those, not just by one of them. So we should get negative 16.67. I know your calculator probably has an ongoing 6 there. You can round it to 1 or 2 decimal places. It's fine. Now our units, we've got joules and joules. Grams and grams will cancel. And we are left with degrees Celsius, which is good because Celsius measures temperature. All right. So that's our specific heat equation. We can use it to measure or to calculate Q, M, C, or delta T. We've seen Q, C, and delta T. The same process would be true for your mass. So just keeping track of those units, being careful on how you rearrange your equation is going to help you. Thanks.